We have all been there. You're trying to push broken shopping cart. You want to go forward, but the wheels are fighting you. You spend 90% of your energy just keeping the cart from crashing into the wall, and only 10% actually moving down the aisle. This is exactly how stochastic gradient descent behaves in high-dimensional space. It fights the terrain, it wobbles, it crashes, but modern AI, the models like GPT-5 and Claude, they don't use broken shopping carts. They use an engine that adapts to the road, accelerates through the curves, and corrects its own mistakes. Today, we are going to build that engine and we are going to learn why Adam isn't just an optimizer, it's a physics simulation that powers the intelligence revolution. What's up everyone? Welcome back to Sumantra Codes, and I'm Sumantra. I have spent years deploying machine learning systems into the real world. I have worked on different kinds of things where the optimizer needs to converge in microseconds to massive generative adversarial network or GANs that takes weeks to train on a cluster of high-end GPUs. And here is the brutal truth that most tutorials won't tell you. Your model architecture doesn't matter if your optimizer is broken. You can have the most beautiful transformer architecture in the world, but if you're using vanilla SGD without understanding the landscape of your loss function, you're going to burn thousands of dollars in compute time just to watch your loss curve flatline. Today, we're doing a definitive deep dive. We aren't just going to import torch.optim, we are going to derive the mathematics of momentum from classical mechanics. We are going to understand why RMSProp was invented in a Coursera lecture, not a research paper. And we are going to solve AdamW mystery, why the most popular optimizer in the world had a critical bug for 3 years that nobody noticed. If you're ready to stop guessing hyperparameters and start engineering convergence, let's get to the board. Before we can talk about the solution, we have to respect the problem. We're trying to minimize the loss function j theta. In high school calculus, you learn to find the minimum of parabola. You take the derivative, set it to 0, and boom, you found the bottom of the bowl. But in deep learning, we aren't optimizing a 2D parabola. We are optimizing a function with billions of parameters. We are operating in a billion-dimensional space. And in this space, our intuition betrays us. We face 3 distinct enemies. The enemy number 1 is the local minimum. This is a small pothole in the mountain, and if your optimizer is dumb, it falls into the pothole, thinks it reached the bottom of the ocean and stops, and it gets stuck. The enemy number 2 is the ravine. Imagine a long, narrow canyon. The walls are extremely steep, but the floor of the canyon slopes very gently downwards. If you are a gradient-based optimizer, you look at the walls and say, wow, that's steep. Let's go that way. So you jump towards the center, but because the step is too big, you overshoot and hit the other wall. Then you look back. Wow, that's steep too. So you jump back. You end up oscillating, bouncing back and forth between the walls while making tiny, pathetic progress down the river. This is the shopping cart wobble. And the third enemy is the saddle point. This is the most dangerous one in high dimensions. Imagine a horse saddle. In one direction, front to back, the curves goes up. In other direction, left to right, the curves goes down. At the dead center, the gradient is 0. It is perfectly flat. If your optimizer relies solely on the gradient being non-zero to move, it will stall here. It thinks it's finished, but it's actually sitting on a ridge, not in a valley. Our goal is to build an algorithm or an agent that can navigate this hostile terrain. It needs to ignore the potholes, stop bouncing off the ravine walls, and escape the saddle points. Let's start with the baseline stochastic gradient descent. The equation is simple. Theta nu is equal to theta old minus alpha times nabla of j theta. Theta is our weight, nabla j is the gradient or the slope, and alpha is the learning rate. In modern usage, the term SGD is used loosely to mean mini batch gradient descent, which we discussed earlier in the series, a variant of gradient descent in which small batches of training data are used at a time. So over here, we are referring mini batch gradient descent as stochastic gradient descent or SGD. So SGD is a stochastic because we don't calculate the gradient for the entire data set at once, which would be pure gradient descent. We take a small batch, say 32 images, and calculate the gradient for that batch. This introduces noise. The gradient for batch 1 might point north. The gradient for batch 2 might point west. The gradient of batch 3 might point northeast. On average, these noise cancels out and we move towards the minimum. But step to step, it looks like a drunken walk. We are stumbling around. If the learning rate alpha is too small, we'll take millions of years to reach the bottom. If alpha is too big, we will explode. We'll jump so far that we'll fly out of the galaxy. This is the fatal flaw of SGD. It has no memory. Every single step is a fresh start. SGD doesn't know that it just came from the left wall. It doesn't know that for the past 50 steps, we have been trying to move downstream. It only cares about right now. It lacks context. And in intelligence, context is everything. How do we fix the zigzag? We look at the physics. Imagine a heavy bowling ball rolling down the ravine. If the ball hits the left wall, does it instantly stop and turn 90 degrees? No, it has inertia, it has momentum. It might turn slightly, but its heavy mass keeps it moving in the general direction of the valley floor. The oscillation is damped. We can simulate this mathematically by introducing a new variable which we call velocity or v. In standard SGD, our velocity was just the gradient. In momentum, our velocity is a combination of the past and the present. So we have the equation velocity at time t is equal to beta multiplied by velocity at time t minus 1 plus 1 minus beta multiplied by gt. Theta new is equal to theta old minus alpha dot vt. Let's break this down. This is an exponential moving average. Vt minus 1 is our previous velocity, beta is our friction coefficient, and it's usually taken as 0.9, and gt is the current gradient. The equation says the new speed is 90% of the old speed plus 10% of the new slope. Think about what this does in the ravine. So, in vertical direction or in the walls, the gradient points plus 10, then minus 10, then plus 10, then minus 10. What is the average of plus 10 and minus 10? 0. The momentum cancels out the zigzag. The velocity in vertical direction goes to 0. The horizontal direction or the river direction, the gradient is plus 1, plus 1, plus 1, plus 1. The momentum accumulates. It builds up speed. We stop bouncing and start accelerating down the center of the valley. This is why momentum is so powerful. It acts like a low-pass filter. It ignores the high-frequency noise or the jitter and locks onto the low-frequency signal or the trend. If you're using SGD without momentum in 2026, you're essentially driving a car without shock absorbers. Momentum fixes the direction, but we still have the problem with the scale. We are using the same learning rate or alpha for every single parameter in our network. Imagine you're training a language model. You have some words that appear constantly like the, and, is. These parameters get massive updates every step. You have other words that are very rare like apoplectic or boustrophodon. These parameters might only see a non-zero gradient once every million steps. If you set your learning rate low enough to keep the stable, the word apoplectic will never learn. It moves too slowly. If you set your learning rate high enough to teach apoplectic quickly, the word the will explode and destroy your loss function. We need an adaptive learning rate. We need a mechanism that looks at each parameter individually and says, hey, you change a lot, I'm going to slow you down. Hey, you rarely change, I'm going to speed you up. This is RMSProp, or short for root mean square propagation. It was unpublished for years. only existing in a slide deck from Geoffrey Hinton's Coursera class. Yet, it became the backbone of modern AI. The equation of RMS props are ST is equal to beta multiplied by ST minus 1 plus 1 minus beta GT square, and the theta nu is equal to theta old minus alpha divided by square root of ST plus epsilon multiplied by GT. Look at the GT square. We're squaring the gradients. Why? Because we want the magnitude. We want to know the energy of the gradient, regardless of whether it's positive or negative. ST accumulates this energy. It tells us how steep has the terrain been recently. Now look at the update rule. We divide the gradient by square root of ST. If the history ST is huge, steep terrain or frequent updates, we divide it by huge number. The step size shrink. If history ST is tiny, a flat terrain or a rare updates, we divide by a tiny number. The step size grows. So RMSProp acts like a normalizer. It forces the loss landscape to look like a perfect bowl. It stretches the flat parts and squashes the steep parts so that optimizer can move at a constant, confident speed in every direction. So we have two great ideas. Momentum accumulates velocity to smooth out the path, first momentum, and the second is RMSProp, scales the learning rate to handle the sparse data, which we can call second momentum. In 2014, King Ma and Ba asked why not both, and ADAM, adaptive moment estimation, was born. ADAM is literally just momentum plus RMSProp combined into one update rule. So the ADAM equations are MT is equal to beta times MT minus 1 plus 1 minus beta 1 multiplied by GT, which is a momentum, and Vt or a velocity is equal to beta 2 times multiplied by Vt minus 1 plus 1 minus beta 2 multiplied by GT square, which is RMSProp, and theta nu is equal to theta old minus alpha divided by square root of Vt plus epsilon multiplied by Mt or momentum. See what happened? Instead of stepping by the raw gradient G, we stepped by smooth momentum M, and we normalize that step by smoothed variance V. So the next thing is the bias correction trick. There's one detail that separates from juniors from the seniors. When we start training, we initialize M, V to 0 vectors because beta 1 is usually 0.9. The first update is M1 is equal to 0.9 multiplied by 0 plus 0.1 multiplied by G. Our estimate 0.1 G, it's tiny. It's biased towards 0. We don't fix this. The model will barely move the first few thousand steps. It's like a cold engine. Adam introduces a correction factor. M hat t is equal to mt divided by 1 minus beta 1 t subscript. At step t equal to 1, this becomes m1 by 0.1. It multiplies our tiny estimate by 10, scaling it back up to the correct magnitude. As t gets large, beta t goes to 0 and the correction disappears. It is a warm-up mechanism built directly into the map. So Adam was great. It became the default. But there was a problem. For years, researchers noticed that for state-of-the-art results on ImageNet, simple standard gradient descent with momentum was still beating Adam. Adam converged faster, but SGD generalized better. Why? The answer lay in L2 regularization or weight decay. In classical SGD, L2 regularization or adding penalty to the loss and weight decay or subtracting a bit of the weight every step are mathematically identical. W new equal to W old minus alpha multiplies by G plus lambda W. But in Adam, remember we divide by the variance square root Vt. If you add the L2 penalty to the gradient G, Adam scales it down. For parameters with high variance, the weight decay is crushed, and for parameters with low variance, the weight decay is boosted. This is wrong. Weight decay is supposed to be gravity. Gravity shouldn't change just because you are running fast. In 2017, Loshilov and Hutter proposed AdamW. The change is subtle but profound. Decouple the decay. So, first thing is to calculate the standard Adam update without regularization. The next thing is to apply weight decay to weight separately. So, theta is equal to theta minus Adam step and theta is equal to theta minus alpha lambda theta old. By pulling the weight decay out of the adaptive loop, we restored its power. This simple change allowed transformers, BERT, GPT, or VIT to train stably. Without AdamW, the large language model revolution might have stalled. If you're importing torch.optim.Adam today, you're likely making a mistake. Switch to torch.optim.AdamW. It is the same algorithm, just with the math fixed. We have covered a lot of ground. We went from bouncing shopping carts of SGD to the precision guided missile of AdamW. Here are three things you need to etch into your brain. First, momentum gives the optimizer memory. It smooths out the noise of mini batches and helps you barrel through local minima. It turns zigzags into straight line. Next, RMSProp handles the scale. It ensures that rare parameters learn just as fast as frequent ones. It flattens the mountain and lifts the valley so the optimizer sees the level playing field. And the third, Adam combines both. But remember the W. Standard Adam breaks weight decay. AdamW fixed it. For 99% of the modern deep learning tasks, especially transformers, AdamW is your starting point. I want to hear from you in the comments. Have you ever spent days tuning a learning rate only to realize you were using the wrong optimizer? Or have you seen AdamW lift in your own validation curves? So let me know below. That's it for today. I'm Sumantra. This is Sumantra Quotes, and keep engineering intelligence.